Welcome one and all to the exciting world of Practice Exam 1B. Dun-dun-dun, dun-dun-dun. First, we have a problem about the ever-important reaction profile diagrams. So the first thing we want to notice here is that we have a positive delta E. So we're looking at an endergonic reaction here. So right off the bat, we can eliminate three of these choices. C, which is exergonic, B, which is exergonic, and E, where the energy doesn't change overall, and that's called isogonic. Next, we want to compare the relative activation energy with our delta E to see which of these remaining choices could be correct. Notice how our activation energy, E sub A, is substantially greater than our overall energy change delta E. In fact, it's about 2.5 times more. So we need to make sure that the reaction profile diagram that we choose adheres to that relative change. With choice D, we can see here that the overall energy change is more than half that of the activation energy barrier. So this one's not looking so good. But let's take a closer look at choice A. Here, our proportions look just right. In fact, if we were to calculate the relative amounts, every hash here would be about 5 kilojoules per mole. So choice A is both endergonic and it has the right proportions between our activation energy and our delta E. So it's choice A for the win. Up next, we have a question about relative rates, aka stoichiometry in action. So the first thing we want to do is look at our rate of formation of NO2. The problem tells us that we're making 3.7 times 10 to the negative third molar NO2 for every second. Now, all we need to use is the stoichiometry of our reaction to find out what that translates to with respect to the decomposition of N2O5. We can see here that we get 4 NO2 for every 2 N2O5 we use up. So we're making this at twice the rate that we're using this. So then, using dimensional analysis and stoichiometric coefficients, we can say that we get 2 molar of we use up 2 molar of N2O5 for every 4 molar of NO2 that we produce. Units cancel out. So a relative rate of disappearance of N2O5 is 1.85 times 10 to the negative third molar per second, or choice B. On this next problem, we want to see how changing concentrations of reactants will change the rate based off of our rate law that we're given. So here's our rate law. What I like to do for problems like these is just imagine everything is originally 1 molar. Poof! Wham! Now let's just see mathematically what would happen if we make the changes that the problem suggests. We're tripling the concentration of nitric oxide, and the concentration of everything else is remaining the same. So, mathematically, the rate would go 3 squared, or 9 times as fast. And indeed, that's what we would expect if we were to triple the concentration of something that is second order. Because remember, the second order means that there's an exponential relationship between the concentration of the reactant and the rate. This next problem wants to find the units of K. It's purely dimensional analysis problem looking at our rate law. Just remember that we want our rate to be in molarity per unit of time, in this case seconds, and our concentrations are going to be in molarity. If you just plug in units, then you'll easily get the units for the rate constant K. So we're going to rate our rate law just using the units. So molarity per second is our rate, equals our rate constant K, that's what we're solving for the units for. And then we've got molarity to the 1/2 times molarity to the first. So I'm just going to rewrite this as molarity times seconds to the -1 equals K. And then molarity to the 1/2 times molarity to the first mathematically will give us molarity to the 3/2 power. Now all we have to do is to divide both sides by molarity to the 3/2. So molarity to the 3/2 will cancel out on the right hand side. And molarity, which we can also think of as just being molarity to the first, divided by molarity to the 3/2, will end up getting us molarity to the -1/2, and nothing happens with our seconds. It's still s to the -1. And those are going to be our units for K. This next question is about what do enzymes do? Or what do catalysts do? So A says decreasing the energy of the products. An enzyme does not do anything to change the relative energy of the reactants and the products. They're still the same reactants and the same products. So A is not true. The way an enzyme or catalyst works, though, is by decreasing the activation energy of the reaction. So it can give us an alternative route to reach the products. Here we can see that if the dotted line represents our catalyzed reaction, the activation energy of our catalyzed reaction is substantially less than the activation energy of our uncatalyzed reaction. So notice our delta E of the reaction remains unchanged. The only thing that changed here are our transition states, our activated complexes, which in turn lowered our activation energy. So it's important to know that this is how catalysts function. They lower the activation energy of the reaction to make it easier to get to the products, which in turn speeds up the reaction. It does not shift equilibrium to make one side more favorable than the other. It does not change the temperature. Changing the temperature would do that, which I guess kind of makes sense. And it does not increase the activation energy of the reaction. That would make it go slower. Here we want to know the most likely form of decay of cadmium-116. So cadmium is element number 48, meaning it has 48 protons. And this particular isotope would have 116, the atomic mass, minus 48, or 68 neutrons. So now we want to see why this is imbalanced when we compare it to the most stable isotope of cadmium. Since the atomic number of protons, is not greater than 83, we can rule out alpha decay. So what we want to do is compare our radioactive isotope of cadmium with the most stable isotope of cadmium. Remember that if you look at the periodic table, the mass is skewed toward the most stable isotope. So, since it's 112, we can say that the most stable isotope of cadmium has 48 protons by virtue of being cadmium, and 112 minus 48 are 68 neutrons. Now, just compare our stable isotope of cadmium, cadmium-112, with our radioactive cadmium-116. What's the issue? Well, if we compare it to the stable isotope, cadmium-116, well, there's too many neutrons. So that means this is going to be an ideal candidate for beta decay. In this problem, we're balancing a nuclear reaction. So we just need to keep in mind the conservation of mass. So there's 6 rounds of alpha decay. Here we have our alpha particle. There's 6 of them. And there are 5 rounds of beta decay. And then we have some mystery isotope M. What could it be? Let's find out. So we just need to make sure that the left-hand side of our equation and the right-hand side of our equation are balanced in terms of both the atomic numbers, which you can find on the bottom, and the atomic masses, which you can find on the top. First, let's figure out the chemical identity of our mystery isotope. Let's find out what element it is. So, we'll set the atomic numbers of the reactants, which is just 92, equal to, we've got 6 alpha decays, so 6 times 2. Each alpha decay takes with it 2 protons, plus 5 times negative 1, plus y. So, after a little algebra, we will get the atomic number equals 85, which means our element is none other than astatine, AT. Now, let's figure out what isotope it is. We're going to do the same thing that we did before, except now we're going to be looking at the numbers on the top, our atomic masses. So, 238 is equal to 6 times 4 for each alpha decay, plus 5 times 0. Technically, beta decay does not change the atomic mass of the nucleus appreciably, plus x, the atomic mass of our mystery isotope. Solving, we get x equals 214. So now we know the exact chemical identity of our mystery isotope. It is astatine 214. In this problem, we're given a plot of the natural log of concentration versus time, and we'll notice here that if we look at all of our data points, they're all nice and in a row. So, what does this mean? Anytime you plot the natural log of concentration versus time and you get a straight plot of data, it means you are definitively dealing with first order kinetics. That's not what an E looks like. If we consider the first order integrated rate law and we compare it to slope-intercept form of a reaction, y equals mx plus b, you should see that first order reactions should afford us a linear trend when we make this plot. So that's indeed the situation, which means this is first order. So what other important piece of information can we glean from this graph? Well, note the slope is negative 0.014 seconds to the negative 1. Well, what does that mean? Is that the same value as one of our important constants? Something fundamental for a reaction? Yes! Our slope is equal to negative k, which means if we have the slope, we have our k. Huzzah! So considering slope equals negative k, that means that for this reaction, our k is 0.014 seconds to the negative 1. And now we have all the information we need to solve this problem. Recall that for first order kinetics, half-life, T1/2, and K are fundamentally related. So half-life is equal to 0.693 divided by K, which means if you know one, in this case K, you can find the other. So, plugging in our K, we will get that half-life is equal to 49.5 seconds. Choice D for the win. This problem asks us to figure out the activation energy of a reaction, given some information about the reaction, that it's 4 times faster at 50 degrees Celsius than at 25 degrees Celsius. So anytime you're trying to relate the relative rates of a reaction with 2 different temperatures, there's only one equation on our data sheet that relates activation energy, rates, and 2 different temperatures. And that is the Arrhenius remix that you'll find right here. Very, very useful equation. This equation can look somewhat imposing, but as long as you don't try to plug in everything at once and take your time, it's really not bad. So one of the things that I like to do is I'd like to take a note of which temperature is the hotter temperature. For consistency's sake, I always like to make T1 the hotter temperature, which means a faster reaction, which means a greater value for K. And we'll see why it's helpful to make T1 the higher temperature in just a second. Please also remember that units are really important. Whenever we plug into the Arrhenius equation, we want to plug in terms of Kelvin. So we're going to need to add 273 to our temperatures that were given in degrees Celsius. Also remember that K1 divided by K2 is just the ratio of how many times the faster the reaction is at temperature 1 than at temperature 2. And this is the reason why I always like to make temperature 1 the higher temperature, because generally speaking, these questions will be worded as how many times faster is a reaction. How many times slower just doesn't make as much sense. Now, let's plug in, solve, and enjoy. So we'll have the natural log of 4, how many times faster the reaction is at the higher temperature, is equal to activation energy, which we're solving for, divided by our gas constant R, 0.008314 kilojoules per mole Kelvin. I plugged in the kilojoules version of this because generally speaking, when we're solving for activation energy, we're solving for kilojoules. Times, in parentheses, 1 divided by 298 K, our temperature 2, minus 1 divided by T1, 323 K. Now, let's take this one step at a time and figure out our answer. Kelvin will cancel out. I always like to get rid of these parentheses with the temperatures in the denominator first. Ends up being 0.000260. And then the natural log of 4. So the natural log of 4 is 1.39. And now we're just going to multiply through R and divide each side by 0.000260. And we will get 44.3 kilojoules per mole, our answer.